simplifying radical expressions, which will help when we get to 9.4, which is solving quadratic equations with square roots or with the square root method. So yay for that. Just a reminder, 8.4 through 8.6 work was supposed to be all turned in yesterday. If you didn't get it in and you still have work to do, one of the other intermediate algebra teachers forgot to let her classes know that. So I will accept it through the weekend, but after Sunday night, if it's not in, it's not in, and it's going to go to a 0. So make sure you get any work from the end of chapter 8 turned in if you haven't done so already. Excuse me. All right, so a radical expression is an expression that contains a square root. Another name for a square root is a radical. A radical is simplified when it contains no perfect square factors other than 1. So it will always contain a perfect square factor, but it will always be 1. We want to get all the other perfect square factors out. So we're going to list the first 20 perfect squares in this table so that you can refer to them. So we would have 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Eleven squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, 16 squared is 256, 17 squared is 289, 18 squared excuse me, 324, 19 squared, let's see, 361, and 20 squared is 400. Sorry, I just ran, I couldn't, I ran out of room. So I had to write a few underneath. Now, a few ways you can check to make sure that these are the perfect squares. If you remember our step pattern for x squared, we go over 1, up 3, up 5, up 7, up 9, up 11. So if you look at the odd integers, you should be able to add them to your previous answer to get your next one. So 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16, 16 plus 9 is 25, and so on. So adding 11, 13, 15, 17. So as I got up to these larger ones, you'll notice I just kind of took a minute and looked. I was adding the next odd integer so that I knew what I needed to add to my previous answer to get my next answer. I do have the first 16 memorized, just because when you work with them, it becomes kind of easy to memorize them. But you have that table, and if you fill it out in your packet, then you'll have it for anything you're working on for this chapter. So the numbers 1, 4, 9, 16, 25, those are the perfect squares. All right, so there are two methods for simplifying perfect squares. The first method involves making a factor tree, and the second involves finding perfect square factors. I'll be honest, I like the second method. Both of them work fine. I prefer the second method, but make a factor tree for the number under the square root. Keep breaking down the factors until you are down to all prime numbers. So remember, prime numbers are numbers that are only evenly divisible by 1 and themselves. Circle all the pairs of factors. Box the leftover numbers that could not be paired. Pairs go outside the radical, 1 per pair. So if you have a pair of 2s, you would put a 2 outside the radical. The box numbers go under the radical, and then multiply the factors outside the radical and inside the radical for it to be simplified. So here's an example, 80. And the way that I would do it, I would just start with 2 and see if it works. So 2 and 40. Then I'm going to try 2 again, 2 and 20. Then I'm going to try 2 again, 2 and 10. Then I'm going to try 2 again, 2 and 5. And 5 is a prime number. So I'm going to circle my pairs. And I like to do it this way. There's a pair. There's a pair. Box the remainers. All right, then outside of my radical, I'm going to have a 2 and another 2. Underneath my radical, the only thing boxed was the 5. Multiply 2 times 2 is 4. So the square root of 80 simplifies to 4 times the square root of 5. That's the factor tree method. It's great, especially if you know your prime numbers. It works really well. The second method is to first find the largest perfect square that divides evenly into the number under the radical. Rewrite the radical as a product of your perfect square from step 1, simplify by taking out the perfect square. So in this case, I'm going to think of this as, and there, this says rewrite it as a product. What I like to do is rewrite it as 2 radicals. And this radical is going to contain only perfect squares. And this one will be the ones that are not perfect squares. So I'm going to put my perfect square list up again. Okay, so whoops, that's not going to be very good. I'm going to okay, that's what I want. So try this again. So I look for perfect square less than or equal to 80. I mean, if 80 is a perfect square, I'm done. I can give the answer. But the largest perfect square that's less than 80 would be 64. Now I check, does 64 divide evenly into 80? And the answer is no. You can check that on a calculator or whatever. So you're just looking, 80 divided by 64, do I get an integer answer? 80 divided by 49 does not work. 80 divided by 36 does not come out even. 80 divided by 25 does not come out even. 80 divided by 16, oh, that does come out even. 80 divided by 16 is 5. So there are my perfect square and non-perfect square. And the square root of 16, well, 16 is 4 times 4. So the square root of 16 is 4. And I'm done. There are other ways to go about simplifying radicals. Some people look and they say, okay, if it's not a perfect square, I'm going to start with the perfect square that is the largest one that's less than half of that number. And you can do that. It works out mathematically. It's okay. I personally don't want to miss anything. So I maybe check a couple extras. All right. So I will show both methods. I think we've got 6 examples here that we're going to do. I will do the first set using the tree method and the second set using that largest perfect square method. So the square root of 75. 2 does not divide evenly into 75, so I can't use 2. 3 does, because 7 plus 5 is 12. And 12 is evenly divisible by 3. 3 doesn't divide into 25. Excuse me. But 5 does. And 25 is 5 times 5. So there's my pair. And that's the only number that's a non-pair. So 5 root 3 is equal to the square root of 75. Letter B, divide by 2 because it's even. We get 54. Divide by 2 again, we get 27. 27 isn't even, so now I'm going to divide by something else. I'm going to divide by 3. 27 divided by 3 is 9. I'm going to divide by 3 again. So I have that pair and that pair, and that one is the one that doesn't have a pair. So I get 2 times 3 times the square root of 3, and 2 times 3 is 6, square root 3. All right, this third one is a little different because we already have a 3 out front. And the nice thing is it doesn't change the way we're going to do the problem. We're still going to approach it with one of our two methods. I'm going to do the tree diagram, but what I need to remember is there's already a 3 outside of the radical that I will multiply my pairs by to get my final answer. 32 is even, so 2 divides evenly into 32, gives me 16. 16 is even, 2 divides into 16 to give me 8. 8 is even, 2 divides into 8 to give me 4. 4 is even, 2 divides into 4 to give me 2. Here are my pairs. I have 2 pairs of 2s. So I have 3 times 2 times 2. One of those 2s from this first pair, the second 2 from the second pair. And I have this other 2 that doesn't have a pair to go with, so it goes underneath the radical. 3 times 2 times 2, that's 12. Radical 2. All right. Questions there? All right. So now 3 other ones. You can in your note packet, you'll see we did 108 as letter B. So we're going to do 72 for letter D. So the first thing I do check, is 72 a perfect square? The answer is no. So then I'm going to look for perfect squares less than 72. So 64 is less than 72. And I'm going to check. Does 64 divide evenly into 72? And the answer is no. So then I check the next perfect square, which would be 49. Does 49 divide evenly into 72? No. So the next perfect square is 36. Does 36 divide evenly into 72? The answer is yes. So I have 36, which is a perfect square, and 2. The square root of 36 is 6. So there is the square root of 72 can be simplified into 6 times the square root of 2. Notice I'm not just plugging in 72 in the calculator and taking the square root and writing out the decimal approximation. So don't do that on your homework either. I want expressions that possibly contain square roots. They might not. If we had a perfect square factor, it would not contain a square root. 5 times the square root of 40. So now I have that 5, and I've got possibility of perfect squares and non-perfect squares. So the first perfect square that is the largest perfect square that's less than 40 would be 36. And so I check, does 36 divide evenly into 40? No, 40 divided by 36 gives me 1.1 repeating. Then I check 25. Does 25 evenly divide into 40? No. That would be 1.6, I believe. The next perfect square is 16. Does 16 divide evenly into 40? No, that would be 2.5. So then I check the next perfect square, which is 9. Does 9 divide evenly into 40? No, that would give me 4.4 repeating. Then my next perfect square would be 4. And 4 divides evenly into 40. So we go 4 and 10. The square root of 4 is 2. So just like with the tree method, I need to multiply my 5 and my 2. So 40 divided by 4 was 10. 10 is not a perfect square, and it's not evenly divisible by a perfect square. Uh, 99. So again, checking, is it a perfect square? No, it's close, but it's not quite there. So then check perfect squares less than 99, like 81, not evenly divisible by 81. 64, not evenly divisible by 64. 49, almost, but not quite. So it's not evenly divisible by 49. 36, not evenly divisible by 99 is not evenly divisible by 36. 25, 99 is not evenly divisible by 25. 16, 99 is not evenly divisible by 16. 9, yes, 99 is evenly divisible by 9. The square root of 9 is 3. And that 11 is not a perfect square. So 3 times the square root of 11 would be our answer on that one. All right, I'm going to give you just a minute. Write down which method do you prefer, the tree method or the perfect square method, and then summarize how you use that preferred method. So just a quick write to get some ideas down. All right, so that writing is actually for your own benefit. Now, a couple for you to try using your preferred method. So go ahead and try to simplify these two radicals. And again, I'll give you a couple of minutes, and then we'll look at the answers. All right, if we take a look at these two examples, just trying to get my timer out of the way. All right, so again, I'll do the first one with the box method. I'll do the second one with the perfect square method. So we have that 4 out front. 2 goes evenly into 98 because it's even, and it goes in 49 times, or 98 divided by 2 is 49. if I divide, let's see, 2 does not divide into 49. The next prime number would be 3. 49, if I add the digits, it adds to 13. That's not evenly divisible by 3. 5 is the next prime. 49 does not end in a 0 or a 1, so 5 doesn't work. 7, we just have to try. And 49 is evenly divisible by 7. It's actually 7. 49 divided by 7 is 7. And I'm done. Now I have my perfect squared factors and my non-perfect square factors. So, and the key is to remember which goes where. So I put one perfect square factor outside of the radical and all of the non-perfect square factors inside the radical and multiply if I need to. In this case, I don't need to. There's my answer. All right, 261. Oops, using the perfect square method. Let's see. So 16 squared is 250. Oh, 261, first of all, I should check, is it a perfect square? And I do not believe it is. So then I should check 256 is the largest perfect square that's less than 261. But 261 is not evenly divisible by 256. So then I check the next one, 225. That's not going to work. 196 isn't going to work. I skipped one. Nope, 196. Okay. 169 isn't going to work. 144 is not going to work. 121 is not going to work. 100 doesn't work. 81 does not work. 64 does not work. 49 does not work. 36 is not going to work. 25 won't work. 16 will not work. We're running out of choices here. 9, if I add the digits together, I get 2 plus 6 plus 1. That's 9. It is evenly divisible by 9. And let's see, that would be 229. So that one was tough, just to find a perfect square that works. Square root of 9 is 3 and 29. You know, actually, if I would have done those two in the reverse order, it would have been probably easier. There's one thing I forgot though on the first example, and one of you probably, at least one of you probably noticed, I hope. I forgot about the 4 that was out in front. So 4 times 7 is 28, square root 2. If you ever notice something like that, let me know. It's okay to say, hey, Mr. Gingrich, I think you left that out, and I would appreciate it. All right. There is a multiplication property of square roots. If, and I like it kind of the other way around, but the square root of a times b is equal to the square root of a times the square root of b. In other words, what I can do is if I have these square roots, I can multiply what's underneath. So 3 times 21 is 63. And now I should factor to see if 63 has any perfect squares. So let's see, 2 does not divide evenly into 63. So I don't have to try 2, but 3 does. And look at that, wow, 3 divides into 63 21 times. I can see that right from here. And 3 divides into 21 7 times, and 7 is prime. So now I've got my pair, I've got my non-pair. So my answer would be 3 times the square root of 7. If you have numbers outside, you can multiply them. So in this case, I'm going to multiply the 2 and the 4. And inside, I'm going to multiply the 3 and the 5. Now I want to see if there's a perfect square that evenly divides into 15. So if I use the perfect square method, oops. So the largest perfect square less than 15 is 9. 15 is not evenly divided by 9 or evenly divisible by 9. 4. 15 is not evenly divisible by 4. The only other perfect square is 1, and we really don't use 1 because it doesn't break down that radical. So in this case, 8 square root of 15 is the is your final answer. There were no perfect square factors that we could take out. All right, try this one on your own. All right, so let's take a look at this one. Again, there's a 3 out front, and it's kind of like there's a 1 in front of the root 10. So I'm going to multiply 3 times 1, and 6 times 10 is 60. I'll just use the tree method for this one, although you can use either. 2 and 30, 2 and 15, and 15 would be 3 and 5. So I've got that pair that's perfect squares, and these are not perfect squares. So I would have 3 times 2, and underneath the square root, I would have 3 times 5. And if I multiply those together, 6 square root 15. All right. Excuse me. Your homework is posted along with the note check. So you have about an hour. I will set up breakout rooms. I will meet you there in just a minute or two. And if you have questions, feel free to ask me there.